Okay. All right, so let me take over first. Bartram, Blair, Donnelly, Elwell, Levengood, Miller, Sheffield, Sullivan, and Tillis. And I think there's one person I'm probably missed because he is or she is. Oh, Donnelly, okay. Mr. Donnelly, can you hear me?
Yep, I can hear you.
Okay, good. All right, so we're going to start with chapter 2. And again, and I think I said this before, the first 5 chapters is pretty much a bit of a review. So I'm going to go through them quickly. So that includes the current chapter that we're going to start now. Let me do this here. Okay, so that. Large. All right, so a bit of a review here with respect to certain terms that you should be familiar with: atoms, molecules, and ions. And the first thing we're going to talk about here is the law of chemical combination. And what this law says, well, I should say laws of chemical combination. And there are a couple of them, the first of which is the law of conservation of mass. And basically what this law says is that the total mass remains constant during a chemical reaction. Pretty much what that means is that whatever the amount in terms of mass of the products you end up with will be equal to the mass total of the reactants you started off with. And then there's another law which you may or may not have met before in your previous chemistry experience, the law of definite proportions. And basically what it says is that all samples of a compound have the same composition, all right? Or another way of saying it is that all samples have the same proportions by mass of the elements present. So basically what this is saying is that if you have a particular substance, and it doesn't matter how you arrive at that substance, if you got it from nature or if you made it in a lab, basically its composition by mass would be the same. So a good example of this would be water, right? Water is about 89% oxygen and 11% hydrogen, right? And that is true for every single sample of water. It doesn't matter where you get it from, right? If you get it from the river or out of space or from your tap, it doesn't matter. The percentage will remain fixed for that particular substance, all right? So here's another example. Now, this compound, I don't remember what it is. Basic copper carbonate. Okay. So basic copper carbonate has these percentages for the different elements that make it up. You have copper, you have carbon, you have hydrogen, and you have oxygen. So those are the percentages. And as you can see here, there are different sources of it shown here, but basically they all have the same composition, and that's because they're the same substance, right? So the composition is fixed for any particular substance, all right? Now, let's look at this example here. It says the mass ratio of oxygen to magnesium in the compound magnesium oxide is 0.6583 to 1. So the question is asking, what mass of magnesium oxide will form when 2.00 grams of magnesium is completely converted to magnesium oxide by burning it in pure oxygen? So in order to answer this question first, what we need to, what did I do? We need to find out what the mass of the oxygen that reacts with the given amount of magnesium. So they gave you this ratio here, which is the ratio between the oxygen and the magnesium in this particular reaction. So since you're starting at 2.000 grams of magnesium, then to find the mass of oxygen, I will multiply that by a conversion factor, which represents this ratio right here. So it is it is oxygen to magnesium. So what they're saying here is at 0.6583 grams of magnesium will react with 1 gram of, I'm sorry, this should be oxygen. 0.6583 grams of oxygen will react with 1 gram of magnesium. So let me get my cheap calculator here. And again, as always, please do the calculations along with me because I could be totally mistaken in my work here. But this is what I got for the mass of oxygen. I got 1 point, how many 6 figs? 4 6 figs. So 1.317 grams of oxygen, right? So that's a mass of oxygen that will combine with the 2.00 grams of magnesium. So therefore, the total mass of the magnesium oxide form would be equal to the mass of the magnesium, which you started off with, which is 2.000 grams, plus the mass of the oxygen that reacts with it, which would be 1.317 grams, and that will give you the answer. So all I have to do here is add 2 to this, and the answer would be 3.317 grams. And that will be the final answer. All right? Okay, any questions about this? Any questions about this example? Any questions? Okay, moving along. Another law that deals with the combination of elements to form a compound. This law is called a law of multiple proportions. And it's kind of wordy, so let me just read it and then explain what it's saying. It's saying that when 2 or more different compounds of the same 2 elements are compared, the masses of one element that combine with a fixed mass of the second element are in the ratio of small whole numbers. So let me try to explain what this statement is saying. What this statement is saying is that if you have the possibility of 2 or more different compounds formed between 2 elements or more elements, then if you keep one mass of, or if you keep the mass of one element fixed, then when you look at the ratios of the other elements, it would be some whole number ratio. So it could be like 1 to 2 or 1 to 1, or well, not 1 to 1, 1 to 2 or 3 to 1 or 2 to 3, something like that. All right. So that's basically what this law is saying. So just to illustrate what we're talking about here, to demonstrate this law, let's look at 2 compounds that are formed between carbon and oxygen, right? One is carbon monoxide, the other one is carbon dioxide, right? Now, if you were to make, let's say you start off with 3 grams of carbon in each case, right? And you're trying to make carbon monoxide and carbon dioxide from 3 grams of 2 separate samples of 3 grams of carbon. Then what will happen is that the mass of oxygen required to make, to react with the carbon here to form carbon monoxide will be 4 grams. Whereas in the case of carbon dioxide, for the same mass of carbon, the mass of oxygen required will be 8 grams, right? So basically, in terms of the total mass of the compound that will be formed in each case, in the case of carbon monoxide, the total mass will be 7 grams. In the case of carbon dioxide, the total mass will be 11 grams. And what they're looking at here is the ratio of oxygen to carbon, which in this case here, all you have to do is divide it 4 by 3 to get this ratio. And here divide 8 by 3. But the important thing I want to point out here is this. If you look at the mass ratio for the carbon dioxide, which we got here, and divided by the mass ratio for the carbon monoxide, then basically you're going to end up with the mass ratios of the oxygens that are present in each of these samples of carbon, again, provided that you started off with 3 grams of carbon in each case, right? And you'll notice here that that ratio works out to be a 2-to-1 ratio, right? So that's a whole number ratio when between the oxygens, when the carbon is fixed for each of the compounds, in the case of carbon monoxide and in the case of carbon dioxide. And that should come as no surprise, because if you look at the formula for carbon monoxide compared to carbon dioxide, you'll notice that you have a subscript of 2 right here, right? Whereas you only have a subscript of 1 here. So therefore that will indicate, and of course there's only 1 carbon atom in each case in the formula. So therefore that will indicate that the mass ratio between the oxygen and carbon dioxide compared to the oxygen and carbon monoxide would be 2-to-1, provided that the mass of the carbon is fixed. And you can see this in other examples. In fact, if I'm not mistaken, I think I have another example of 4 compounds. Okay, here it is. So in the case of this example here, there are 4 different compounds, 4 different oxides of nitrogen that can be formed by combining 28 grams of nitrogen with differing amounts of oxygen. So assuming that you're starting off with 28 grams of nitrogen, there's one compound that would form if the amount of oxygen that it reacts with is 16 grams. We call that compound 1. In compound 2, the mass of oxygen that would react with the same mass of nitrogen would be 48 grams. And in the case of compound 3, the mass of oxygen that would react with 28 grams of nitrogen, the same mass, would be 64 grams of oxygen, right? And there's another one, compound 4. In the case of compound 4, the amount of oxygen that will react with the nitrogen, same mass, 28 grams of nitrogen, will be 80 grams, right? And if you compare these numbers here, again, the mass of nitrogen is fixed. The amount of oxygen that is reacting to form different compounds will be different. But if you look at the ratios, what do we notice, right? In other words, the question is being asked here. What's the ratio here? 16 to 48 to 64 to 80. So what's the ratio? Anybody? The simplest ratio, let's put it that way.
Would it be 1/3?
Well, no, I'm asking for the ratio. Like, you know, this is 16, 48, 64, 80. But we can represent this ratio in a more simple way by dividing by a certain integer. What do I call it? The highest common factor or something like that. It's a long time since I've done that, so I don't remember all those terms. So what would be the highest common factor? I think that's the right term.
Wouldn't it be 16?
Exactly. So if you divide right through by 16, what do you end up with? 1 here, and here you end up with what? 3, and here you end up with what?
4,
Exactly, and here you end up with what?
5.
Right. So it's a 1 to 3 to 4 to 5 ratio as far as the masses of the oxygens are concerned for a fixed amount of nitrogen, right? And if you look at the formulas for these compounds, these are the formulas right here. And what do we notice? The number of nitrogen atoms remain the same in each of the molecules, but if you compare the oxygens, the number of oxygen atoms, it's 1 to 3 to 4 to 5, all right? So that's basically what this law is saying, right? If you have 2 or more compounds that can be formed by the same element, you keep mass of one of them fixed, then the ratio of the others would be according to some small whole numbers. Okay, so that's the law of multiple proportions. Then we're going to go quickly through Dalton's atomic theory. This is something I know you should have met before. This was put forward by an English school teacher by the name of, I forgot his first name, Dalton, in 1803. And he basically came up, well, let me give a little preview first before we get to Dalton. So basically from way back when, and I don't know the dates, that's why I was never a history major. But if you're talking about back in the days of the Greeks, right? They were wondering, and the idea was put forward that if you take any substance and if you could possibly break it down into its simplest unit, then you know that unit would represent basically all the other atoms or particles, right? The term that the Greeks came up with to describe the smallest unit, they called it atomos, and from that we get the term atoms that we use every day, right? Of course, there's been some time passing between when the Greeks first put forward this, and then later on, in 1803, based on accumulated information concerning how substances behave, Dalton came up with his theory to explain a couple of things that we observe, namely the law of conservation of mass and all the other laws that we talked about earlier, the law of definite proportions and the law of multiple proportions. So here's another situation where the scientific method is working out, right? The law basically describes what is observed, but of course, in chemistry, as in all other scientific disciplines, we are also concerned with explaining what we observe in terms of a natural phenomenon. So Dalton came up with his atomic theory, and basically, I'm just going to go through the postulates of his theory, the first of which is that matter is composed of atoms, which are tiny, indivisible particles. So that was the first postulate that he came up with. Let me just say here that we now know that this is not entirely true, right? We now know that while atoms are tiny, they are not indivisible because you can actually break them down into simpler fragments. And you can go all the way down to the fundamental fragments, namely the protons, the electrons, and the neutrons, right? So again, this is one of those things that is observed in science when it comes to the scientific method. Somebody may come up with a theory, and the theory might be believed for a while, and then, of course, later on, people make discoveries, and one of the discoveries that was made in this particular case is that there are even smaller particles that are located within the atom, right? So we're all aware of that now, so therefore we know that this particular postulate is not 100% true. Okay, let's look at all the others. So the next assumption is that all atoms of a given element are the same, all right? Which we now know to be true. Atoms of one element differ from atoms of another element. That is true too, right? If you compare, let's say, hydrogen to sodium, they're different. They have different masses and so on and so forth, right? Compounds are formed when atoms of different elements unite in fixed proportions. We now know that to be true as well. And a chemical reaction involves rearrangement of atoms. No atoms are created, destroyed, or broken apart. So that's basically what I just described here, is basically what Dalton's atomic theory is all about. And for the most part, it is true in all cases, excepting what I mentioned before, the fact that we now know that atoms are divisible. They tend to stay intact in chemical reactions, for example, but in the case of nuclear reactions, which we won't be covering in Chem 1, if you have to do Chem 2, you'll definitely cover that. What you'll find is that in nuclear reaction, you can actually have, for example, a nucleus splitting apart, breaking down into smaller fragments, and in so doing, create new elements, all right? But in chemical reactions, that doesn't happen. Okay, so that's Dalton's atomic theory. And just to delve into this theory a bit more in terms of the reactions of substances and what happens at the microscopic level, here we're looking at the reaction between, and let me write down the equation here. The reaction here is between hydrogen and fluorine to give hydrogen fluoride. And of course, based on this equation, there's a 1:1:2 ratio, mole or molecule-wise, between hydrogen, fluorine, and hydrogen fluoride, respectively, right? So this is basically the equation for the reaction. Now here, we have a situation where we have 2 hydrogen molecules, right? And we have 3 fluorine molecules. Now, because of the 1:1 mole ratio that exists between the hydrogen and fluorine, as described in this equation, we know that 2 of these molecules will react with 2 of these fluorine molecules, which means that 1 fluorine molecule here will be left over. So therefore, based on the equation, we can predict that the total number of hydrogen fluoride molecules will be 4, which are over here, and we'll have a fluorine molecule left over, all right? So this is something, even though we're not dealing with this particular topic right now, but this basically illustrates the concept of limiting reactants, right? Again, this is something you should have met in your high school or introductory chemistry, where one reactant is used up completely, and that would be the limiting reactant. That determines how much product you expect to get. And then you have one of the other reactors, which is left over, which would be the excess reactant, which in this case would be the fluorine. But that's not the point I'm trying to get to here. The point I'm trying to get to here is that even though the fluorine here, this molecule did not react, if you look on this side, the total mass is conserved, right? And the reason why the total mass is conserved as you go from reactant to product is because the atoms themselves are not created nor destroyed as you go from left to right, right? So therefore, basically, you started off with 6 fluorine atoms, you're going to end up with 6 fluorine atoms on the left side. If you start off with 4 hydrogen atoms on the right side, on the left side, then you're going to end up with 4 hydrogen atoms on the right side. So the point I'm getting at here is that this demonstrates why the law of conservation of mass is obeyed. And that's because the law of conservation of mass says that the total mass is conserved. Total mass of the reactants will be equal to the total mass of the products, or the mass is not created nor destroyed in any chemical reaction. And the reason why that is true is because the atoms themselves are not created nor destroyed in any chemical reaction, right? So that's basically how the Dalton's atomic theory actually explains the conservation of mass law. Okay, enough of that. So let's delve into what I alluded to earlier, the subatomic particles. As I said before, we now know that the first postulate of the theory that Dalton put forward is not true entirely because atoms are divisible. You can actually break them down, as I said before, into more fundamental particles. And these are the particles you all should know about already. The protons and neutrons, of course, are located within the nucleus, while the electrons are spread around the nucleus in a more diffuse way. And this table here basically summarizes the location and nature of these particles. So the protons has a relative mass of 1 and a charge of +1, and it's located in the nucleus. The neutron has a mass of 1, so it's approximately the same mass as in the case of the proton, but the size, or I should say the charge here, is 0 for neutrons. Of course, as implied in the name, it's neutral. And it is also residing in the nucleus. And then we have the electron, which is much lighter. As you can see here, this number here is significantly smaller. If I'm not mistaken, this is 1/1800. So basically what we're saying here is that the mass of the proton or the mass of the neutron is approximately 2,000 times greater than the mass of the electron. The charge on the electron is -1, and the electrons, as I said before, are located outside the nucleus. Okay, then we get to isotopes, another term that you should be familiar with. Isotopes are basically atoms that have the same number of protons but different numbers of neutrons. And one key thing you need to remember is that isotopes are basically of the same element because they have the same atomic number. Remember, the atomic number is what basically defines what the element is. But you can have two atoms of the same element and they have different numbers of neutrons. And because they have different numbers of neutrons, their mass numbers will be different. So just to recall the atomic number, again, another term you should be familiar with. The atomic number is the number of protons in the nucleus of an atom. And the mass number is the sum of the number of protons and neutrons in the atom, all right? And conventionally, we use the letter Z to represent the atomic number and A to represent the mass number, all right? And of course, if you know the mass number and the atomic number, you can easily determine the number of neutrons by simply subtracting the atomic number from the mass number, and that would give you the number of neutrons. Okay, some other things about isotopes. I'm quite sure you're familiar with this representation. We call this the isotopic symbol, right? Where A is the mass number, as we said before, which is written as a superscript. Z is the atomic number, which is written down here as a subscript. And then the symbol for the element is where E is. So here we have two examples of isotopes of chlorine. We call this chlorine 35 and this chlorine 37. And based on simply given this information here, you can tell something about the composition of the element in terms of the fundamental particles. So for example, you should be able to answer this question. How many protons are there in chlorine 35? How many protons are there in chlorine 35? 17, exactly. Because 17 is the atomic number, which by definition is the number of protons. How many protons are there in chlorine 37? 17 again, exactly. And that's how isotopes are. They have the same atomic number, which means that they're of the same element. Here's another question. How many neutrons are in chlorine 37? 20, exactly. The difference between the mass number and the atomic number will give you the number of neutrons. Okay, very good. Okay, so here's another example. How many protons, neutrons, and electrons are present in a bromine 81 atom? So how would you answer this? What would be the first thing you would do? Anybody? How would you get the number of protons? Let's start off with that. Exactly. Where do you get the atomic number? From the periodic table. So what's the atomic number of bromine? According to the periodic table over there, it is 35. All right. Okay, so for the protons, that will be equal to 35. What about the neutrons? Come on, guys, this should be a breeze. I'm sorry? And how do you get that? Well, it's the atomic number from the mass number one. Yeah, right. So that gives you 46. Very good. And what about the number of electrons? Exactly. 35. For a neutral atom. Of course, when we get to a discussion of ions, things are a bit different, but you're right. In any neutral atom, the number of protons would be equal to the number of electrons. Okay, so that's a relatively simple example. Any questions? I don't think there should be any questions about this. So let me move on. Okay, another term. And again, this is one of those situations where people tend to confuse one term with another. In this case, we're talking about the atomic mass, right? But before we get to the actual concept of atomic mass, of course, we can all appreciate that atoms and even particles smaller than atoms, their masses are very small, all right? And therefore, a lot of the conventional units that we'd use to express the masses of regular size objects becomes a bit inconvenient when it comes to recording and expressing the mass of small particles. So therefore, we need a unit, a special unit that is basically what we use when it comes to expressing the masses of such particles. So it's called the atomic mass unit, AMU, right? In some textbooks, you just see the letter U, right? Same thing. And it is defined as seen here as exactly 1/12 the mass of the carbon-12 atom or isotope, all right? So that's the definition, right? Based on that definition, then pretty much that unit or that scale is used to express the masses of small particles like atoms and ions and protons and neutrons and so on. Okay, so that's the atomic mass unit. And it turns out that that atomic mass unit is equal to this value expressed in grams. So as you can see, if you're going to use a gram unit, it's a very small number because you have 1.66 times 10 to the minus 24 grams, all right? And for all purposes, we're just going to round this out to 3 sig figs. In fact, the table that I've posted in Canvas expresses it as 1.66 times 10 to the minus 24. So that's what we're going to use for all purposes, all right? So that shows you how small the atomic mass unit is, all right? Now, one thing I want to say here, and unfortunately or fortunately, we won't get into it right here, is this statement right here. And it might seem a bit counterintuitive when you see this for the first time, right? It says that the mass of an atom is not exactly the sum of the masses of the protons, neutrons, and electrons, all right? One would think that if you have an atom like, let's say, just use a simple example, let's say carbon, right? Carbon has an atomic number of 6, and let's say we're dealing with the isotope where the mass number is 12, then you'd expect that the mass of that atom would be the sum total of the masses of all the particles, the protons, neutrons, and electrons in it, right? And that makes sense. I wouldn't blame anybody if they're not familiar with chemistry. I wouldn't blame anybody who would come to that conclusion. However, we now know that is not true, right? And all I can say is, without getting into any deeper detail, is that you have to wait until you get to nuclear chemistry and general chemistry 2 to understand the reason why. That's all I'm going to say about that, right? Because it's a bit involved. But basically, I just want you to know at this point that, you know, the mass of the particles in an atom is not equal to the total mass of the atom itself, right? So that's, you know, for those of you who have to do Chem 2, then you're going to learn the reason why that is not the case. Okay, continuing our discussion of atomic mass. So here we have a question that I want you to ponder and tell me what you think the answer is. The question is, do all isotopes of an element have the same mass? Let's deal with that first. Yes, no, no. Okay. So the next question is why or why not? Well, since we know the answer is no, why not? Because, exactly, because you have different numbers of neutrons, and therefore that would affect the masses of the isotopes, all right? So here's a key thing I need to explain to you, which, as I said before, students tend to confuse some terms here. So if you look at any legitimate periodic table, such as the one over there, right? There are 2 numbers associated with each element. One of them is the atomic number, which we defined already, right? The atomic number is the number of protons present in the nucleus of an atom. The other number is what we call the relative atomic mass, or they simply just call it the atomic mass. But more accurately, to be perfectly honest, it should be called the relative atomic mass. That number represents what we call the weighted average of all the masses of all the isotopes for that particular element. And that is based on what we call the relative abundance of the different isotopes. So I'm going to explain what that means shortly. But the key thing I want to say at this juncture is that please do not confuse the atomic mass with the mass number, right? Those are two different things, right? Students tend to confuse one with the other, right? Remember, the mass number is simply the number of protons and neutrons present in the atom, right? That's a mass number. And that would be an integer based on that definition, right? But the weighted atomic, the relative atomic mass or the atomic mass is a different thing, all right? It is not, it is dependent on the mass number to a certain extent, but it's not exactly the same thing. So we're going to get into how do we determine the weighted average atomic mass, all right? Now, the best way to explain it, in my opinion, is to go directly into an example. So here we have an example of two isotopes of carbon. And let me just say this. This here, right here, represents what is called the relative abundance expressed as percentages. And let me explain what these two numbers mean. Basically, if you take any sample of carbon, right, naturally, let's say a piece of coal or a part of an organic molecule or something, what you'll find is that if you could separate the isotopes of carbon, the percentage of carbon-12 in that isotope, or the percentage of carbon-12 isotope in that sample, would be 98.892%, and the rest would be 1.108%. And there are some other isotopes as well, but their percentages are real small. So we're just going to stick to these two, right? So this basically would be the percent abundance of each isotope for any sample of carbon that you pick up anywhere, all right? So that's the percent abundance, and this is basically the same thing as this. The only difference is that they're expressing it as a fraction. Okay, now here's a question to illustrate how we get those numbers, and we're just dealing with carbon in this case. It says, use the data cited above to determine the weighted average atomic mass of carbon. The atomic mass of carbon-12 is, and it gives you the value, 12.00050 after the decimal point AMU, and that for carbon-13 is 13.00335 AMU, all right? So let me show you how this is done. What I'm going to do here is I'm going to start off with the carbon-12, C12. And what I'm going to do here is to multiply the mass of the carbon-12, which is 12.00000 AMU, multiplied by the fractional abundance here, which is 0.98892. And then I'm just going to set up for the other one, carbon-13. I'm going to multiply the mass of carbon-13, which is 13.00335 AMU, by the percent, or not the percent, the fractional abundance, which is 0.01108. And then let's do the calculation here. So the first one is 12 multiplied by 0.98892. And according to my calculation, that would be equal to how many sig figs here? So the lowest number of sig figs will be 5. So I got 11.867 AMU. And then for the next one, I'm going to multiply 13.00335 by 0.01108. And I got, how many sig figs here? 4 sig figs. So that would be 0.1441 AMU. And then what I'm going to do is add these two together. So I'm going to add 11.867 to 0.1441. And the answer I got here, and in this case now, because we're adding, we have to round off to the lowest number of decimal places. So I got 12.011 AMU. And that would represent the weighted average atomic mass of carbon, taking into account not only the masses of the individual isotopes, but also the relative percentage or abundance of the separate isotopes. So that's basically all those numbers that you see there for the atomic masses of all the elements. That's how they're determined, right? Based on the relative abundances of the isotopes and the masses of the isotopes, all right? Any questions about this? Any questions? Any questions? Any questions? Okay, let me see what's next. All right, so before we get to the next topic, I think it is best that I hand these out to you. And Mr. Donnelly, I don't remember if I am, hold on, let me see. Oh, are you still there? You're saying that he might lose a signal. I guess he's lost a signal. Anyway, what I'm going to do is provide, hold on, let me see here. I'm going to post assignment 2 for him so that he will have access to it. And I'm going to hand it to you guys right now. And I want you guys, for now, focus on questions numbers 1, 2, 1, 2, and 3. Questions 1, 2, and 3. I'll be right back. Okay, it's almost time, so what questions have you guys gone to so far? Oh, three? Oh, that's interesting. I thought you guys would have some issue with actually question number three. All right, well, hold on to the assignments. And we'll continue this discussion on Tuesday. Let me remind you that assignment one is due today. If you have it here with you, you can submit it now, but you can also submit it online. And remember to submit it as a PDF document if you so choose to submit it in Canvas.